lecturing is dry work. Okay, I'm going to talk about GSAS-II a little bit, some details of how it operates and what it's all about. Yes, installation of GSAS-II. I think if you've not installed GSAS-II, what you need to do is simply go to the web and search for GSAS-II. Don't search for GSAS. And the reason is because you'll get an awful lot of Graduate School of Arts and Sciences. And also the Greater Seattle Aquarium Society. And a lot of other things like that. So if you search for GSAS-II, you'll get GSAS-II and nothing else. And there is a website that gives an enormous amount of information about GSAS-II. Everything from, you can get at some of the documents that we have for it. And there are installation kits for Linux, Windows, and Mac OS X. And as far as I know, what they will do is they will install Python, its own particular version of Python, and GSAS-II in a directory of your choice. You do not need to have administrative privileges in general to do this unless your institution is really tight-fisted. Places like Los Alamos, for example. Anyway, the other thing I want to point out here is that there are tutorials. There's more than 50 of them that cover various aspects of GSAS-II in its operations. If you're interested in anything that you want to do, go look at the tutorials. There's usually more than one tutorial that covers a particular topic. So for instance, if you're interested in magnetism, there's 5 tutorials that cover doing magnetic structures inside GSAS-II. There's 2 for texture and so forth. I strongly recommend you do that. You have to have internet access for this, for looking at the tutorials, but once you've downloaded the tutorial and the files, you don't need the internet access anymore. The other thing I want to say is update often. We change GSAS-II literally daily. The current version is something like 5,400 and something or other. And so that and it started at 1, so you can imagine how many times we have updated the software. We operate not on a release series of kind of thing, which is what a lot of software does. If someone tells us about a bug, we fix it and make that the new version immediately. Because we don't want people to try to work with a buggy version of the software if we can avoid it. And if we've got some bright idea about something to add to GSAS-II, we add it and then release it immediately. Bugs and all. So be prepared for that. If you encounter a bug, the first thing to do is update and try it again, because we may have fixed it. Okay? And then if it's still there, please tell us so that we can look at it. We may very well ask you to send your project file, and I'll talk about what a project file is in a few minutes, so that we can try it out as well. These files are not very big, so you can send them. Okay. Right. And as I think I pointed out, you can install it anywhere. Where did I say that? Yeah, you can even put it on a memory stick. It works from that. Okay, what is it? It's a modern piece of software. A modern GUI. The GUI tends to look like the operating system GUI. So a Mac window will look like a Macintosh window. A Windows window will look like Windows, and the Linux will depend on what your project, what your window manager is. The features of it is that there is a main menu, which appears on this side of this little line. On a Macintosh, it's up on the main window for the whole thing. This is for Windows and for some flavors of Linux. So this is the main menu. It's got things like file, data. Under calculates things like refine, do the read belt refinement. Also under there is absorb and F prime, which calculates absorption corrections, things like that. We talked about that earlier. On the other side of this line is commands which are specific to whatever is being displayed here, and it will change from time to time depending on what you have selected. On this side of the frame is the tree of data, which has an entry for each data set that you have in here, whether single crystal, powder, diffraction, reflectometry, or what have you. There will be an entry for each one here, and it will then have sub-entries depending on what it is that characterizes some feature of that particular data set. Comments, by the way, for powder diffraction are whatever was on the raw data file. They're simply copied into the comments so you can actually look at them. Sometimes it's nothing, and sometimes it's hundreds of lines of stuff that's been tacked on the front of the data set. That typically comes from a synchrotron. Because of what might be in there, crucial bits of information like temperature, something like that, maybe. Identity of the sample, if you're lucky, and so forth. So anyway, that's that. And phases, there'll be entries under phases, which are the multiple phases in your sample that you put into your sample. In this case, it's just one. The tab then, this main part of the window then is determined by whatever you pick here. So it will change every time you make a different selection out of the tree. And for phases, you get multiple tabs of information, 10 or 12 of them, depending on what it is. The general tab is the one that usually shows up first, and it's got things like the lattice parameters of the space group, a description of the contents of the unit cell, and some controls for general things down below, Fourier map controls and so forth. So these things all change every time you change the tab or whatnot. What our purpose in doing that is to reduce the clutter on the window. A lot of software I've seen have a lot of buttons that don't seem to have anything to do with the data. We try to get rid of that by this process. Okay, the plots. The whole point of the plots is that every time you've got information which is numeric, I want to show you a picture of whatever it is. So obvious things are powder patterns, which you can then zoom in on. If you've got multiple data sets, you can create so-called waterfall plots, which look like this. You can shift the relationship between one data set and the next, so globally. You can shift them to the left, to the right, or up or down. Alternatively, you can draw it as a contour plot, which looks something like this. For the crystal structure, you can draw polyhedra, balls and sticks, ellipsoids for temperature factors, and things of that sort. And if you generated a Fourier map, there is this display which shows a slice of the map, which is drawn through this point, which is, by the way, known as the viewpoint for the drawing. And it is a plane which is perpendicular to your viewing direction, which is that. And as you rotate the structure, the map changes to go along with that. That's only if you have a map. Okay, more. If you do microstrains and you refine one of these generalized, this is the so-called Popa-Stevens model. And by the way, I call it that because Popa actually described it before Peter Stevens. So it's the Popa-Stevens model, or it should be anyway. And you might be interested to know what these numbers represent. Well, it's a surface that looks something like this. And so that gives you the microstrain surface. If it's isotropic, it's a ball. If it's uniaxial, it's an ellipsoid, and so forth. If you do texture analysis, you can draw pole figures and inverse pole figures rather than having a whole table of spherical harmonics coefficients. It's sort of meaningless to anybody. Okay. On a slightly different matter, and this has to do with two-dimensional images collected, say, at a synchrotron, where you put up an image plate in front of a sample, and the X-ray beam goes through the sample and puts rings on the plane. Well, what happens if the plane is tilted? And it always is. And it could be tilted by a lot. It could be displaced as well. Well, the question then is, where's the incident beam on the detector? Because that's going to give you the origin of the image. Well, there's some programs out there. Fit2D is one, something called Data Squeeze is another, which gets this wrong. Because what they've assumed is that the diffraction, the incident beam is at the center of the ellipse, and this is simply false. And you may ask, well, how do you know that? Well, you have to go back into the literature to 1822. That's 200 years ago. This guy in Belgium actually worked it out. Okay? So in a sense, there's no excuse for getting it wrong. And this is his figure from 1822. And basically what he does is, here's the plane that you're interested in. This is the detector plane. And if you construct two spheres, this one, which is below the plane, contacts the diffraction cone and the plane. Here's another sphere, which also contacts the diffraction cone and the plane, and the centers of these two spheres define the beam. It's simple. And the rest of it is just trigonometry. And the thing about this, GSAS-II uses this. There's not a whole lot of image processing programs that actually do this correctly. It's shocking how many of them get it wrong. And by the way, you might ask, well, how well does it work? Well, here's another rendition of his little figure. But here's an image where the detector was tilted 45 degrees to the incident beam. Obviously, we have ellipses for the diffraction cones. And the fitting by GSAS-II absolutely nails the orientation. And I might add, these little crosses here mark the centers of the respective ellipses. And as you can see, the centers of the ellipses are nowhere near the beam position, which is there. Okay? I don't know if pi phi gets this right. I don't think it does. Yeah, by the way, that's a popular one that people use.
I think that's because we use it for like 30-degree angles.
What's that?
We use it for like 30-degree tilts.
Oh no, there's no limit. I mean,
but yeah, we've used that like extremes.
Yeah.
It works great.
Yeah, you can tilt the detector quite a lot. And there are reasons to do it sometimes, because if you want to go to a higher angle, you might want to tilt the detector to be able to capture a larger angle, larger 2 theta. Anyway, I offer that. And here's a case. The detector is tilted so much that the rings out here are hyperbola. You can't see them, but there are diffraction rings out here. And if you do the integration of this thing out into this region, then, which is beyond this line, these guys are the diffraction rings which are out here in this space. And it's a perfectly good integration. The sensitivity is such that if the detector is tilted by even less than ½ degree, there's an error in the integration. So a smearing of the image. So it's important to get this right. Okay, after you've done the image processing, you can stay in that project and work on it. If you've got a powder pattern, you can do Rietveld refinements or peak indexing or whatever it is you want to do with it. If you've got small angle data, you can, which might look something like this, you can do small angle scattering analysis. And if you've got powder data, you can do a calculation of a paired distribution function, which looks something like this. And this is actually much more developed than this little comment here. People use this all the time for X-ray data, for generating PDFs. For solving crystal structures, the process first involves indexing the pattern, finding out what unit cell belongs to that pattern. And by the way, you don't do this on a mixture. You really need to have a pure material with one set of reflections, because trying to index two overlap patterns is damn near impossible compared to doing a single one. Anyway, so the point is you would fit the peak positions, and then subject to an indexing algorithm inside GSAS-II, which is, by the way, the same as used in Topaz, or a small modification thereof, and works just as well. It's a lot slower, but it works. And so if you do structure solution, GSAS-II does this by charge flipping. So you start with a pattern, you do some sort of intensity extraction, you do the charge flipping, and you wind up with a set of atom positions, which, by the way, a charge flip result has no reference to a space group or anything else like that. The origin is completely arbitrary. And so I use this sort of a trick involving phase relationships in the space group to try to shift the origin over to where it belongs, but it could still be off, so you may have to shift it. Then the next thing to do is identify the peaks as being atoms. And here's the suite of atoms that's associated with this particular structure. And then the next step, what happened? Oh yeah, the next step is to identify the atoms and solve the crystal structure for the atom positions and what the atom types are, and then do the refinement. Reasonably straightforward, sometimes doesn't work. You need data that goes to so-called atomic resolution, which is roughly an angstrom d-spacing for charge flipping to work. Otherwise it doesn't. Okay, the other key, yes?
I have a question regarding this indexing. So how accurate that is? What is the chance that it works properly? Because I'm working on kind of material. I'm using Topaz, same algorithm, and I'm able to index some of the phases, but it doesn't work for all of them. So, I mean, if the things doesn't go smoothly, like with this indexing, what should we do? Is like, because I have seen you have worked with a lot of complicated materials.
Well, one thing is that systematic errors will make it really hard. So if you've got a sample displacement error that shifts the pattern in some way, that makes it much more difficult to do the indexing if they're just not in the right place. If it's a pseudo-symmetry situation where two of the lattice parameters are very similar, so you don't get a clear separation between the peaks, that's hard to index. It's probably important to make sure that one thing that's very important is to make sure you have the very lowest index peaks, that is, the ones with the biggest d-spacings. That's a must. You have to have those in there. Otherwise, it will not index. Because it can't get the big unit cell right without them. What else?
Absorption correction should be applied before we index things.
Sorry?
Like those absorption that we have in the previous presentation.
No, all the absorption does is change the intensity. That really won't matter. But anything that shifts the peak positions will matter. Okay? Yep. That is, what I was going to say before I interrupted myself is that include the little reflections, but make sure your sample's pure. Yeah. One of the probably unique features of GSAS-II is its ability to do sequential refinements. And that is where you have a whole suite of data, hundreds or perhaps even thousands of data sets. And you have a model for the first one, which you then fit to the first data set. You then copy it to the second data set, fit that, copy it to the next data set, fit that, and so forth through the entire suite of data. And GSAS-II then accumulates all the parameters in a table. And when you're done, you can then plot out how a particular value or variable vary as a function of whatever the independent variable is along your data sets. It could be, what you could have done as an experiment where you raised the temperature and then lowered the temperature on something, or just simply raised the temperature, and you want to know how does the lattice parameters change with respect to temperature. So you can get a plot from that. Then at the end, you can actually take that plot and fit functions to it to get things like equations of state and so forth from the variation of the temperature, the lattice parameters with respect to temperature. It will do situations in which the change in temperature has resulted in a phase change, and you get a new phase at some point, where you can do the sequential refinement so it goes through the phase change and into the new phase with a new set of parameters being added to your problem. You can then plot them out and see how they link up from the old phase to the new phase. And you can do this through multiple ones. It's a little complicated to do that, but you can do that kind of calculation. So here's an example. This is just peak fitting, and there's about 5 or 6 different kinds of refinement that GSAS-II will do sequentially. Peak fitting is one of them, and this is an example in which there are 800 powder patterns collected over about 13 hours at a neutron time-of-flight source on a piece of steel that was progressively stretched and compressed. Repeatedly, it was stressed by doing that. And so what you might expect to happen, here's the experimental layout. And what you might expect to happen is that the peaks will shift one way and then the other way because of the load that you put on it. The intensities may vary for various assembly reasons, and you can track all that by looking at single peak fits as a function of load in this case. So here's the pattern, and we're just going to fit the first 6 peaks and ignore the rest of that. And we're going to do that same thing for all 800 patterns. Here's the 800 patterns as a contour plot, and you can actually see the peak positions wiggle back and forth as a function of the loading. There was 2 slow cycles of loading and then a lot of fast ones here. And during this process, actually another phase showed up because the action of that induced the phase change. Actually, what it did is if you look really closely at this, these peaks are here at the beginning, but they're very broad. So what actually happened is that it crystallized the second phase to make it more apparent in the powder pattern. So in this particular case, the big peaks are austenite, and the ones that show up are ferrite, this piece of steel. And if you track the position of one reflection, you can see it as the reflection position shifts back and forth depending on the loading. Okay. And if you look at it very carefully, there is a slight relaxation in the lattice parameters as you put more and more stress on it. You've actually sort of started to ruin it, basically. And if you look at the intensity, first of all, you see the wiggles up and down, but if you look, you say, well, why are there wiggles in intensity? Well, that's because when you put a load on the sample, the crystallites reorient within the sample and you induce texture and change the intensities. And then when you let go, they all wiggle back and you get the fluctuation. And you notice that these are out of phase with those because some go up, others go down. What are all the dropouts? Well, that's when the beam went off. It's the nature of a neutron pulse source. It's not that continuous. Small angle scattering. I noticed that this workshop has a session on small angle scattering. I don't know what software is going to be used, but you can use GSAS-II to do it. And so here is a small angle data set. For those of us who do powder diffraction, you say, well, you know, where are the peaks? Well, it turns out if you look closely at this, there's two bumps. One is here and the other one's here. And that's a characteristic of the fact that this stuff actually has two samples, two particle sizes. Now, the average, the manufacturer said is 500 angstroms and 1 micron. The actual fact of the matter is that one's about 160 angstroms and 1600 angstroms. So it's not what they said it is. So the first thing you can do is a size distribution, which is basically, in a crude sense, is the Fourier transform of that. And then you can, once you've known that, you can put in a model that attempts to fit it. And here's the fit. And it's basically, for all intents and purposes, identical to the data. Notice this is scale here is in powers of 10. So there's a huge range of intensities for small angle scattering, covering, what, 10 orders of magnitude, something like that. So, yeah, and there's a little bit of a background. You can do this sequentially. So here's a sequence of samples that were fit by diluting some colloidal silica. And so you get a range of small angle scattering patterns. And if you fit one of them, you get something that looks like that. And then if you fit all the rest of them, that was one of these ones. I think it was probably that one. And then if you do the rest of them, you can get a sequence of parameters that you can plot out as a function of, say, fraction, or if you happen to know what the composition is, you can put that in and plot it out. Okay, what else can we do with GSAS-II? Incommensurate structures. You might say, well, what the heck is that? Well, most crystal structures, the reciprocal lattice points are in the places that you would expect them on the basis of the size of the unit cell. Some things, and what's shocking about all this is how simple some things are. This is sodium carbonate, and this is a sample. We just simply bought it right out of the bottle, put it on 11 BM, collected a powder diffraction data set. And there are extra peaks in here which are not indexable by the conventional means and lattice parameters. And those are due to a superlattice, basically another dimension on the crystal structure. And it's due to a modulation in the atom positions. And so this is the position of one of the sodium atoms along the y-axis. And as you go from place to place in the crystal structure, it actually wiggles back and forth in a periodic way, and that period does not match the lattice. So in this case, I forget what it is. I think it's close to a third y. Yeah, it's close to a third, but not exactly, or a sixth actually, and close to a third, but not exactly either. And when you draw it out, what you can do in GSAS-II, and there's an option that generates movies, you can show how the structure is modulated. By the way, this is not real life. It doesn't wiggle around like this. These are actually sort of static displacements, but there's a variation as a function of distance to the crystal structure. But this is an attempt to show how it varies, and if you can see the sodium atoms kind of wiggle in an up-down way, and the carbonates do a little rocking back and forth as the sodium atoms. There's also a facility within GSAS-II for reading in incommensurate magnetic SIF files, and you can draw them out. And they do that kind of thing with the magnetic moments. Okay, I'm about done. Yeah, and there's some more examples of the same kind of thing. Okay, capabilities in GSAS-II, and these are the last couple of slides. These are really boring slides. It's a long list of possible things that GSAS-II will do, which includes things which deal with the images, which I've talked about. One of the other things you can do is if you have a sample in which you put some sort of a load on it so that you stretch it in one direction, the diffraction pattern then shows, instead of rings for the Debye-Scherrer cones, they're actually ellipses because you stretched it out in one direction, where you can fit those ellipses and extract out the tensor elements for the strain by the direct analysis of the images. And much of the rest of this stuff is reasonably straightforward. There's two ways of solving crystal structures. One is charge flipping, which, by the way, is a deterministic method. You start someplace and it does its thing. Otherwise, it could be a Monte Carlo method and simulated annealing for solving the crystal structure. You can do structure refinements. This is for powder data. All of these kinds of things. Stacking fault calculations. There's no refinement inside GSAS-II. You can generate PDFs. You can fit the PDFs using third-party software from within GSAS-II for both large box and small box models. And you can do cluster analysis. So if you've collected 1,000 powder patterns on rocks, and you want to say, well, what are all these rocks? Okay, you know, maybe core samples out of a drilling operation or something like that. And so you want to identify what's in there. Well, when you got 1,000 of these things, it's really, you don't really want to go through and try to do every one of them. The first thing to do is take all this data set and subject to a cluster analysis and find out which group of these samples are the same and which ones are different from others. So the cluster analysis allows you to sort of classify them according to just differences in the powder patterns. And then you can go back and look at individual ones to find out, well, what is that group? Okay, and what is that group? It'll save you a lot of time by doing that. Single crystal data. It's got all the capabilities that one has for single crystal data, including incommensurate structures. And you can, the same two methods for solving crystal structures. GSAS-II does not do direct methods. There really isn't much point in having it when you've got charge flipping. It works just about as efficient. GSAS-II knows about twinning models for single crystal data and a more complicated extinction model than you find in, say, shell X or something like that. Okay. Back. Sorry. GSAS-II will do small angle data, which I showed you pictures of. And yeah, there's a whole bunch of methods for that. And it also does reflectometry data, which includes situations where you have created a material in which you've laid down the same kind of layer repeatedly, and you say 25 times, and you say, oh, I should expect to see 25 layers, but I don't know how thick they are. So you can find out how thick they are by fitting them with a reflectometry model. You can do things which involve how does paint dry. Something. Okay. Things for sequential data analysis. As I said before, there's a bunch of different things that you can do. And with the tutorials, this is the last thing I'm going to talk about. As I said, there's 50 of them, and the ones that you should try are this one, and perhaps this one. And this is a combined refinement with X-rays, constant wavelength data. The trick with this one is the two experiments were done at different temperatures. So it tells, this tutorial tells you how to deal with that. And here's another one that does basically the same kind of thing. The two different temperatures, one was room temperature and the other one was liquid nitrogen or something like that. So they're vastly different. But I would do these, and I think Joel has in the third or fourth some other tutorials that cover a lot of the same kinds of things. So I suggest you try those as well. There are more advanced ones, including what to do with sequential data, how to solve crystal structures, modeling and stacking faults, various things with the image, small angle scattering. I don't think I've got one for reflectometry. Sorry, I just haven't gotten around to writing it. And then there's a bunch of other ones. GSAS-II will allow you to do scripting. That is, you can write a bit of Python that accesses the subroutines in GSAS-II to do your own calculation. And this is good for automation of some process where you want to do the same thing over and over and over and over again, but you don't want to do it within the context of a GSAS-II project. Simply because you're just doing it so much. So you can do scripting. And with that, I'm done. Thank you. Go to lunch.
Is there any way that the student gauge space group?
Sorry, I have to go walk around here.
So is there a way that GSAS-II can determine or gauge the space group before peak indexing, or the user have to gauge first?
For the space group, you have to provide a symbol, PNMA, something like that. GSAS-II interprets the symbol itself, item by item, does the group theory and creates the space group operations, all the rest of the stuff from the symbol. So that means you can use non-standard space groups.
So
if it's legal, if it's a legal space group, GSAS-II will interpret it. So it knows what, if there's a space group, FD, okay, well, that's the same thing as CC, but it's got full face centered instead of a diamond glide. And you might ask, well, why do you want to do some crazy thing like that? Well, if that FD structure was derived from an FM3M cubic, then it makes perfect sense to keep the cubic lattice, even though it's been distorted to monoclinic. Okay? And so it knows about, what was I going to say? I mean, there's some nonsense space groups like that you could put in there that it will say, no, that's not legal. So for instance, if someone puts in a space group R2, it will say, because rhombohedral can't mix with two-folds. It's got to be three-fold there somewhere. Otherwise, it is not a rhombohedral.
So the user has to guess the space group from the group theory.
What's that? It does it. It gets the information by doing the group theory. Okay, it's not a lookup. So it's not limited by the limitations of the lookup. Okay. Yeah. Now, by the way, the same thing is true for magnetic structures and incommensurate structures. It does the group theory on the symbol that you put in or find, because it knows how to do that. The other thing too about GSAS-II is it will never ask you for something which it can already have built into a table someplace, like form factors, scattering factors, things of that sort. And it never asks the same question twice. So if you put in the lattice parameters, it's not going to ask you for the lattice parameter somewhere else. It's going to go find it from the entry that you stuck in, from wherever. It will read CIF files, and it will read various and sundry other format files for phases, for structure factors, for powder data. There's an extensive list for powder data from various instruments. And the same thing is true of images. It will import images from all sorts of places, including Mars. Okay?
Any other questions? Well, if not, please. Help me thank the speaker again. Bob, thank you. Now, we are breaking now for lunch. Lunch is served in the same room in the second floor. There are vegetarian options for vegetarians. And we will be back here at 1:15 for one more lecture in the afternoon. And then the rest of the afternoon, we will go to the computer room on the third floor. The computers, you log in with your NSID and passwords. You ask persons, ask them the